this represents a normal building without any structural resilience in it. So you'll have the columns and you have your beams that are going across. The structural support is only the beams and the columns. So when we have an earthquake, what can we do to actually fix that? We're going to put on some cross bracing. This one, as you'll notice, is just a loop. So if you push into it, it's not going to do anything, but if you pull, it's quite strong. So when we put them in these directions, when the building goes this way, it will hold it tight, and then we'll have another one this way. So when the building goes this direction, it will also pull it tight. So we'll show you one direction first, and then we'll put both. Now we put cross bracing in one direction, I'll show you what it does. So when we have a building and we're pulling it this way, you'll notice that the strings aren't doing much, and the building is still moving quite a lot. But when we try pushing the building that direction, the building doesn't move. The pull is getting pushed on these wires, some tension, and it's not going anywhere. So you can see the difference? So now I'm going to show you what it's like when we put the cross bracing on both sides. First I'm going to pull it like I did before. I'm pulling pretty hard and it's not going anywhere. I'm going to push it and it's still not going anywhere. So if we had a big earthquake, pushing and pulling, this is much stronger than it was without the cross bracing. The great thing about Christchurch is the architecture has changed so much since the earthquake, and everywhere you look are examples of different cross bracing. This is the Ernest Rutherford building at the University of Canterbury. As you can see from the outside, you can see cross bracing throughout the entire building. So the big X's were just like we showed with the example. When the building goes this way and when the building goes that way, the cross braces help it keep straight. So what you normally think with cross bracing is an X, but actually it can be a lot of other shapes. As long as it's facing this direction and this direction, it doesn't matter where. So here you can see a good example. So instead of having this, it's just translated this way. But if you think about pushing the building that way or pushing the building that way, it's still holding up with those diagonal bracing. We can also have what we call the K shape. So up here, you still have your direction cross bracing going this way and this way. So it doesn't matter, again, as long as one is going this way and one is going this way, so that when we push the building on either direction, there is that cross bracing holding it up. So one last type of shape is eccentric bracing, where you have the two angles going together, and in the middle you have a joint where they don't fully connect, there's that gap, and that is called the sacrificial joint. So eccentric bracing, when the building shakes, all the forces are pushed into the middle. So if there is any destruction into the building, it will be in that small link, which then can be replaced and the building can be used again.